Thank you very much. I am extremely excited to be talking to you today about writing ridiculously fast F-sharp code, but I want to put that in context because F-sharp is a language that supports a broad spectrum of use cases, and that ranges from the analyst to the high-performance engineer. Now, a little bit of context for those of you who don't know me. I'm a software engineer that works at the company Simulation Dynamics. It's a small company, it's a small consultancy based out of the US that predominantly works with enterprises to optimize supply chains, warehouses, and manufacturing facilities. In addition to that, though, I do run the Fast F-sharp YouTube channel where I provide introductory materials to the F-sharp language, but then provide deep dives on how to maximize the performance of F-sharp. Now, fortunately, with my arrangement with Simulation Dynamics, I am not actually full-time with them. I do have reserved hours that I leave to be able to consult with the F-sharp community. So if you have a project where you need better performance from F-sharp, please feel free to reach out to me. I want to be a resource for the community so that there's never excuse that we need to rewrite it in something like C. Ugh. Okay. So, F-sharp for the analyst. And this is kind of a continuation of some of the talks that we've already had this morning where it discussed why F-sharp is such a good tool for the analyst. And for me, the analyst is a person who's been given a question by the business, and their goal is to answer that question as quickly as possible. Now, what are some of the features of F-sharp that make it great for this use case? The first of all, as we've mentioned in other talks, is that defining types is easy. So if I wanted to create this type chicken, I can give it a few fields, and I can also create discriminated unions, which allows me to describe when I have several things that all might need to be associated together. And the nice thing about discriminated unions is it allows us to cover all the possible cases of a thing instead of using something like inheritance, which you cannot necessarily guarantee that. And so being able to define a nice domain for describing your problem makes it easier for you to reason about your code and how it's supposed to behave. In addition to this, F-sharp has type inference, which gives it the feel of a dynamically typed language while still being statically typed. Now, in this example, the variables A, B, and C are inferred to be integer just based on the use case, but I didn't have to put that in the code. The compiler is doing that for me. Another slightly more complex example is I have this function for creating an instance of chicken. Yes, there are many farm animals in my example because no one gets offended by farm animals, so we're just going to stick with it. The compiler is able to infer that name must be a string, age must be an integer, and size must be a float just based on their usage. So statically typed, but with the ease of a dynamically typed language. We also have pattern matching. And pattern matching allows us to match against data, and what's great about it is that it helps you ensure that your function is total, which is a fancy term for meaning it covers all possible use cases. An example of that is here in this check bounds function. I'm providing a float, I'm using a match statement, but the compiler is smart enough to be able to look at this code and say, you're only covering the negative cases of a floating point number. You should also cover the positive cases. So this helps you eliminate bugs in your code when you're not dealing with all the possibilities that could arise from your domain model. In addition, we have type providers, which allow us to have the compiler look at some data and generate the static types for us. So for example, I could have this in a CSV, and then I can use some F-sharp code, and I'm telling the F-sharp compiler, please look at this data, generate types for me. I don't want to take the time to have to define the schema for it. A more advanced feature of the F-sharp language is computation expressions. And computation expressions allow us to create domain-specific languages for our business problems. One of the reasons this is really nice is as an analyst, you're often thinking in terms of the business, not necessarily computer science. And so when we are able to provide APIs that are in business terms, it reduces the mental overhead of mapping from the business domain to code. And this is actually an example from our discrete rate simulation engine that we developed at SDI. Now, and another thing an analyst is going to love is having a suite of packages that they can import and just start using. I don't want to have to recreate data structures every time I want to use them. So having the .NET ecosystem to be able to leverage from F# is a huge advantage from the analyst viewpoint. Now, there are quite a few other packages inside of F# that would be wonderful for me to unpack, which makes life good for an analyst. But what I want to do now is start to pivot and talk about one of the critical missing pieces that often happens when we have languages that are really focused on the analyst. We make it easy for them to write code, but what about how long it takes that code to run? What is the execution time? And the reason I care about this is the idea of innovation rate. Now, what is innovation rate? It's the rate at which you're able to come up with an idea, implement correct code, and then see the results of that code. And so it's the idea you take the time to develop and you multiply that by the time to execute. And those two things together need to work in concert for you to actually have a high innovation rate. You could write beautiful, succinct code that perfectly describes your domain, but if it takes an infinite amount of time, no one cares. And so a language has to accommodate both of these things. It has to be easy to develop correct code quickly, but that code also must execute quickly. So why is F# a great language for high performance scenarios? Well, to frame this discussion, I want to start with what I think all of performance really comes down to, and that is doing less with less predictably. Okay, I'm going to dive into each of these and give you an example of what I am talking about. Let's first start with doing less. And the idea of doing less is that our code generates efficient CPU instructions. Because at the end of the day, our languages have to be translated down to machine code. And depending on the restrictions of our language, it may be easy or difficult for the compiler to do that. Now, F# is statically typed, which is fantastic for when you need to emit efficient code. Let's look at this very simple example. I have an add function. Type inference is figuring out that A and B must be integers. So even though this might look like dynamically typed code, it is actually statically typed. And that is a very important thing for the compiler because then it is able to say, these are integers. And therefore, it can emit this 86 assembly for performing that operation. It's a Leah instruction. It's a single CPU cycle. You cannot get more efficient than this. Let's contrast that with another popular language. This is almost unfair. So Python, you may have heard of it. It's been used for things, I think, like maybe data science or other things. And we have this very simple example. And I'm not actually going to rag on Python. Python is a fantastic language. It's done a lot of good for the world. But we have this add method. And again, you see it looks very much like F#. It's succinct, it's terse, it's easy to understand, but it's dynamically typed. When the Python interpreter runs, it doesn't necessarily know what these types are ahead of time. So if you actually go to the effort to figure out the x86 instructions that are emitted for this add function, which, remember, this should be equivalent to F#, right? Yeah. Well, we get this, and this, and this, and this. And it's actually not done. There is actually a little bit more, but I didn't want to keep slides going, just looking at all this assembly. And this is fundamentally coming down to the issue that Python, as a dynamically typed language, does not have as much information about the types when it needs to compile code. This is a huge performance penalty. A question that's been going on in the software development community, though, is can you make a dynamically typed language fast? Now, there's been several efforts to do this with Python, one being PyPy, another Unladen Swallow. The most recent one is Mojo. And this is a language that I'm not sure if you would describe it as like a superset or a subset. It's like an evolution of Python. But the idea is that we want to give Python developers a Python-like language that they can work in, which is going to have dramatically better performance. And there are claims of being 10, 100, 1,000 times faster than Python. What's interesting, though, is if you go to their website and look at Mojo code, you're going to notice something very interesting. That looks a lot like a statically typed method there. Huh, interesting. Oh, okay, I want to define a type in Mojo. Man, that sure looks like some typing going into that dynamically typed language there. At the end of the day, what we end up finding is for a dynamically typed language to be fast, you're going to have to start talking in types, man. You're going to have to start telling the compiler this is what this is going to be so we can figure out how to lay out that data and how to emit efficient instructions. Now, let's talk about F#, though. Now, F# performance is interesting because, and this is going to be really interesting because Don Simon is right back there. And so I don't want to say anything that gets me in trouble, but, okay, thank you, sir. Still nervous. The defaults of F# are robust and safe and reliable. They are not necessarily fast, and I'm not saying that's wrong, and here's why. So we have an example of me defining a record chicken, it returns, and then we have this function which is saying equals test. And I have chicken A and I have chicken B, and I'm going to say, is chicken A equal to chicken B? And we will look at the x86 that is emitted for that. That's a lot of x86, I'm not going to lie, for something as simple as an equal operator. And this is actually one of the things that's true across all of .NET, C#, VB, F# as well. Lines of code or number of characters of code can really hide performance penalties. So just because you're using a single symbol for equality does not mean you are emitting the most efficient possible x86 code. And so, and I keep saying x86 code. This goes for ARM. This goes for RISC-V. At the end of the day, all these CPU instruction sets are actually more similar than you might realize. But my point is, that's a single character, and it emits all this code. So if that's how you go about composing your domains and trying to create high-performance code, you're in for a bad time. But, yes, F# has units of measure. Units of measure are one of my absolute favorite features to abuse for all the reasons it wasn't originally intended, or I don't know, maybe Don can correct me. But if you read the paper, is it TOEFL? TOEFL is like the history of programming languages. It talked about adding units of measure to the F# language. Originally, the intention was to verify your algebra. I have found it is incredibly useful for annotating primitives to ensure the correct usage. So now in this case, what I'm doing is I'm going to create a unit of measure, which is chicken ID. And I'm going to use that to annotate integers to indicate what they are meant to represent. And now the type chicken has changed to type chicken data. Because in the reality, that was never actually a chicken. It was just information about a chicken. And now I have this equals test. And you notice that I'm using integers with a unit of measure of chicken ID. How much x86 does this emit? That. Far, far more efficient. Now, a C developer might be laughing at us for working in the .NET runtime because they're like, ha, you work in a managed language. You're going to have bounds checking all over the place, slowing down your code. Well, let's investigate whether that is actually true or not. So I created a very simple test called test. I was very creative, I know, where I'm iterating through an array and I'm accumulating the values. And I wanted to see, okay, what kind of assembly does this emit? And at the end of the day, if you actually look at it, there is no bounds check within this. And the reason is because the .NET runtime is smart enough to know bounds checking is expensive. Maybe I shouldn't do it. So what it's doing is it's looking at what value are you using for indexing into your array, and can I guarantee ahead of time that you are not actually going to go outside of the bounds of the array? So it doesn't need to emit a bounds check at all. So in reality, it's very unlikely you're actually going to incur this penalty. Now, let's talk about working with less. And what I mean is minimizing the memory footprint of our program. Why do we care about this? Well, it comes down to CPU memory architecture. At the absolute center of your CPU is a couple of logic units, one called the ALU, or Arithmetic Logic Unit, or the FPU, Floating Point Unit. And those are where the actual instructions of your program are occurring. But they have to work with some memory, and the only memory they can work with is things held in the registers. And registers are a very finite resource, and believe it or not, there is actually a dot on the screen meant to represent their size, and it's right there. I know it's small, and the reason is because your program is probably going to be bigger than just registers, so it might spill to the L1 cache, the L2 cache, or the L3 cache. You can see that they're getting dramatically larger as we go up the caches. And if we actually want to visualize the size of main memory, I have to scale L3 cache down again to show you how large main memory is. Okay, well, Matthew, you've just explained that we have several caches. Why do we care? Well, it comes down to memory latency. How long does it take for the CPU to load a piece of data from that memory location to a register so that it can actually use it? And this is a visualization of the actual speed comparison between these. Register is instantaneous. L1 takes essentially 3 caches, L2 20, L3 40. Main memory, we are still waiting, typically over 200 cycles for us to retrieve something from main memory. So what does this mean? If our programs are so large that they are constantly spilling out to main memory, we are going to be experiencing that cache hit all the time, slowing our programs down. So what I want you to understand is that cache space is incredibly scarce and should be protected and valued. Now, here's one of the challenges that we have to deal with. The .NET runtime has a garbage collector, and as you see, here's the C dev looking at us in scorn for having a garbage collector. And let's talk about what the garbage collector does. Well, it makes allocating and deallocating memory transparent to us. We rarely have to think about it. It is designed to be general purpose and robust, which makes writing horrendous code in the context of performance easy. Now, what does the garbage collector not do? It does not understand our memory access patterns. It does not co-locate data so that the CPU is able to prefetch data for us so that we're not incurring that cache hit when it has to go out to main memory. And it doesn't have special things like allocation, deallocation, things like arena allocators or things that a C dev would use. Now, you might say like, oh, we're doomed. No, we're not doomed. The talk is not over. We have to think differently about how we allocate and use data in F#. And so I need to introduce you to the workhorse collections for a lot of the code that I do. One of them is row. Row is a struct. It wraps an array, and what it does is it enforces you to use an integer with a unit of measure for indexing into that information. Bar is essentially the same thing, but it is read-only. So what does that give us? Well, it means, in this case, I can create this chicken ages bar. Bar is a read-only wrapper of an array, and it's saying you must use an integer with a chicken ID unit of measure for accessing this data. And so in this case, it's working because chicken index is an integer with a unit of measure, chicken ID. If I try to do that with a different unit of measure, the compiler is going to say, no, that doesn't make sense. And what's beautiful about this is just a compile time check. It is not something that ends up in the .NET code. It will not slow you down. So this is a way for us to maintain domain correctness while only working with raw primitives like integers and floats. So let's look at a common way of laying out data in an F# program. And if you do this, I'm not saying it's wrong necessarily. A lot of this is in the context of when you start really caring about performance. So if you see code like what you've written, please do not feel bad. I do not judge you. So that should not be the takeaway. I'm just saying there's an alternative approach, and I would like to show it to you. Again, we have chicken, and let's say we have an array of chickens. Now, in this case, what's going to happen is each of those elements is going to be another object somewhere out in the heap. Again, the garbage collector is not aware of your memory access patterns, so it could very easily throw those all over the place, which means each time you need to look up a chicken, you are going to incur a cache hit, which is extremely expensive, as we saw before. An alternative approach to laying out our data is to use a struct of arrays. And this actually comes from the video game industry, and they use it pretty extensively because of some other optimizations I will show you later. Quick note, though, this is not a thing you should just do automatically. It should be guided by your algorithms and your data access patterns. It is often faster, though. So instead, what we're going to do, instead of having that array of chickens, I'm going to define this type flock, which is using bar and row to wrap some data and enforce correct units of measure for indexing into it. And so flock is it's this record with 3 fields. Each of those is pointing to an array. Now we only have 3 arrays, and the garbage collector is going to keep all that data contiguous because it is a single array. This will most likely significantly reduce the cache hits that you incur when accessing data. Another common pattern that we might have to deal with is one-to-many relationships. So let's say I have several farms. I have chickens associated with those farms. So the natural way to model that in F# would be something like, again, I have my chicken, and I'm going to define farm. It has a name, which is a string, and it has a flock associated with it, which is just an array of chicken. And here's an example of me creating an instance of that. Now, if we look at the memory layout of this, though, it's going to look something like this. You are going to have your data potentially spread out all over the heap, likely on different cache lines. Again, the garbage collector is not smart enough to look at how your program is running and try to optimize how it's locating things on cache lines for you. An alternative way of dealing with this one-to-many relationship where you have a farm and several chickens is to use this array-oriented way of laying out your data. We're going to have several arrays for our farms, the first of which is going to be names. And so each location in this array is associated with a different farm ID. We have all the chickens that we are going to associate with those farms, but we're going to use this ranges array for indexing into those chickens. And so if I want to know what chickens are associated with a farm, I would go to the range, and then that would tell me what subsection of the chickens array actually belong to this farm. And we still have our arrays for chickens. So how does this actually work in theory? Well, I would take my farm ID, I would index into that ranges, and that range is a struct that has a start and a length, and that tells me, oh, the chickens that are associated with this farm are this subsection of the chickens array. Okay, why would we want to go through that convoluted mess? Well, let's run a benchmark and find out. Let's say I have 100 random farms and 100,000 random chickens. Dear goodness. And I'm going to randomly assign them to farms. And now let's say the work that I need to do is to double the size of the chickens. This is clearly an American feedlot. For those of you familiar with some American farming practices, not proud. So let's measure how long does that take. When we use that original object style that I described before, it would take 1 millisecond to double the size of the chickens. If we use the array style, it takes 24 microseconds. And this is because of the way we've laid out the data. It makes it easier for the CPU to speculate about what data needs to be brought in so it can double the size of it. And what's also exciting about this is because now we're working with arrays of data, it makes another optimization available for us, and that is SIMD, which stands for Single Instruction Multiple Data. And using SIMD has gotten dramatically easier in .NET. It used to be very painful, but it has come a long ways, and it's relatively trivial to do this now. And if I use SIMD instructions, I can get another significant performance improvement. That optimization would not have even been possible with the previous way we laid out data. Now, this is such a common thing that I actually have a few collections that I use for doing this automatically. And there are many other things that I could talk to you about, but I don't have the time. There is a lovely board over there where you can put a sticky note saying, I would like to talk more about optimizing F# memory layout and making things go fast. So if you do that, I would be more than happy to host that discussion, and we can geek out about this as to your heart's content. So your takeaway is that memory layout is crucial for performance. The garbage collector is actually your friend, but you need to help your friend know what to do with the data because it can't figure it out for you because it doesn't understand your program's logic, just memory. And ideal performance is only going to be achieved when you lay out your data in a way that's friendly to the CPU. Let's finally talk about predictably. Writing logic that makes it easy for the CPU to predict what you're going to do. Why does this matter? Inside of every CPU, there's two really important pieces of infrastructure. One is the branch predictor. When there's branches in your code, so if, then, else statements, the CPU is going to guess which branch you're going to go down so that it can start emitting code for the other piece of the CPU to start working on. So the better it is at predicting your code, the better your program is going to run. It also has a memory prefetcher. So you saw that accessing data from main memory was very expensive. Well, the CPU knows that, and so it's looking at your data access patterns and saying, oh, I bet you're going to need that data. I'm going to preload it so we don't have to wait for it later. But that depends on your code being predictable for the CPU. Now, one approach that the video game industry has taken for dealing with this is called entity component system. And this is just a style of writing code. It's not a library you need to get. It's just a way of building up your domain. And the idea in it is that you have an entity, which are the unique items inside of your program or simulation. Components are the data associated with it, things like location, velocity, status. And a system is the logic that acts on components and things like logic for movement or state changes. So we've already seen quite a few examples of what I would refer to as entities. And this is just creating the units of measure for annotating our integers. We've already seen a lot of examples of what components are. It's just the collections of data that go with those entities. So what is a system? Well, typically I will have a namespace called systems, and inside of it, I'll have my module, in this case chickens, which will hold the functions for operating on those components. Now, what you see is that I'm passing in the minimal amount of data for this code to run. I'm not giving it everything inside of my simulation, just the subset that it needs to work on. So what does that look like in a real world system? So this is actually, I know this is, oh, it actually looks pretty good. Right on. So this actually comes from our discrete rate simulation software. And what you see in here is that I have an entities file, I have a components file, and then this entire thing is all the systems that operate on side of them. So it's relatively easy to implement. Why would you use ECS for predictability, though? Well, ECS encourages us to work and operate our data in groups, which makes it easier for the memory prefetcher to load data and to predict what you're going to do. And when you end up acting in bulk rather than individual items, you're able to create smaller loops, which again are easier on the predictor. Now, some of you might be saying, like, Matthew, this is all extremely sus. You've said a lot of things. I don't know what this actually amounts to at the end of the day. Well, let's talk about real-world innovation. So Simulation Dynamics is a company founded by Andy Spirell, and he is one of the original authors of the idea of discrete rate simulation. One of the industry standard tools for doing that type of simulation is ExtendSim, and this is one of their papers where they talked about their cool way of solving these problems. Andy wanted something faster, and I said, how fast? He's like, make it as fast as possible. And I'm like, done, I got you. So using all these techniques that I've been describing here, working entirely in F#, nothing else, we started benchmarking industry standard simulation models, and this is the kind of results that we're getting. So this is actually a much more sophisticated model than I was talking about at JetBrains last year, where the ExtendSim model took 2,600 seconds to run in IDOS, our discrete rate simulation engine, ran in 4. So that means you can do 1.3 simulations an hour in ExtendSim or 900 in IDOS. And this is a visualization for those of you who want to see what the performance difference is. And this actually gets back to the really important point when it came from the data and data science talks. A lot of the time you don't actually have the data you need to do data science with, and so you want a simulation. But if your simulation is so slow, you will never be able to generate the necessary data to start doing things like reinforcement learning. Now we're able to do that kind of things, and this speeds up the rate at which we can improve our systems because we can test and evaluate faster. So what are the takeaways? F# lets you write correct code quickly, and it can achieve C levels of performance. And units of measure are this really essential tool for being able to work with the raw primitives, which are the friendliest thing for your CPU, but still maintain domain correctness. And the performance of the .NET runtime is just getting faster and faster. Any performance gaps that remain with it and C are slowly being closed as new features are added. So finally, I want to say thank you to Simulation Dynamics for letting me come out here and to be able to share all of this. Thank you to the F# community and all of our hosts. Again, I actually do some independent consulting, so if you're having an F# performance problem, please reach out to me. I would love to help you, and thank you very much for having me.